as I mentioned before, this I'm Guy Coleman. I got William Salter and Angus. So the workshop structure: first 15 minutes, do a bit of an intro, then we'll do the assembly for about 50 minutes to an hour. But throughout this, feel free to jump in with any questions in the chat. I just would also ask if you can mute your microphones as well, so we don't get too much background noise. And we'll try and get to those questions for each of the major steps, I guess. So we've got the component and soldering overview. We'll stop there for a little bit, make sure there's no questions there. Then we'll go to the OWL assembly, and we'll then, I guess, make sure there's any issues there or if you have any questions. And then also go through the software setup. So I'll go through, we've already flashed an SD card, but I'll go through the setup on that anyway. Just flashing takes a little bit of time. So we'll just walk you through on a separate screen. Unfortunately, Raspberry Pi can't really install Zoom, unfortunately, or fortunately perhaps. So we'll just have to record the screen from a separate webcam. And then finally, we'll do the field test. So that should be exciting, just out on the patches of turtle or lawn or spotty weeds we've got just over the other side of the car park here in Camden, Southwest Sydney. So that's the structure, and I guess now we'll get stuck into more of the content. And the first thing I thought I'd go through is more the context about the OpenWeedLocator. So just let me see if I can. I think someone's got their microphone on in the background there. If you're able to mute that. That should be cool. So site-specific weed control is all about just finding where weeds are and then only applying the weed control to the weed. And as you'd be aware, probably the most obvious or first step for site-specific weed control is herbicide application or spot spraying, as you might have come across. And this is a rough diagram of that system. So we have the sensor or the camera that detects some sort of information about this environment. It could be a reflected sensor, or it could be a camera, which is an imaging sensor, or it could even be a distance sensor if you're using height to determine what is a weed or what isn't. There's actually research on LiDAR and the use of even sonar and sort of small ultrasonic sensors for weed detection. Then that information is passed to a processor, which in our case could be the Raspberry Pi, which we'll be going through today, or it could be other simple processors or more complex ones as well. And those processors then run some form of algorithm, and that's where the weed detection occurs. And then once the weed has been detected or a decision made on the presence or location of weed, then a controller, which in our case, I guess, is this relay board, that then activates the solenoids or for spot spraying or some other form of weed control. For more precise methods like lasers, that controller might be really complicated and have its own set of algorithms to target weeds. But in our case, for the spot sprayer, or yes, for the OpenWeedLocator, to do spot spraying, it's just a simple on-off relay board. And then finally, you obviously have the control delivery. So obviously, in the case of the OpenWeedLocator or the OWL, the sensor is that image camera, the low-cost camera we've got, and the rest of it, I guess, as I've explained. The next part of the step is, because we're using cameras, it's important to work out how computers actually see. So computers, I guess, and cameras, specifically digital cameras, are usually red, green, and blue. They have 3 channels. So on the left here is, I guess, on these 3 images here, we have the same image 3 times. But what we do, we can extract that into each of the 3 different channels that makes up that image we see on the screen. So we have the red channel, the green channel, and the blue channel. And so within a camera, on the camera sensor, there are little, I guess, electronic, devices that are sensitive to each of these different parts of the spectrum. And when they come together, they can make a complete image. And the way they are sensitive to this is I guess, they take in the amount of light that for each of these channels, and the intensity of that light means how much red there is or how much green there is. So really green stuff will have high intensity in the green channel, as you can see on these green leaves of the wheat. And in the blue channel might not be so much, because I guess plants are often blue, but blue is part of that color. And so that's why there's some blue being reflected. And so what you can do is extract all this information from the image and convert it into pixel values. And so each part of the image, or each layer of these red, green, and blue channels is a pixel, is comprised of pixels. So when you hear of a 14 megapixel camera, that's 14 million pixels. And this has obviously been scaled down a lot so we can visualize it. But what we have here is each of these small or very large pixels, I guess, small in this image, has a value of the reflectance for the red channel and has a value for the reflectance of the green channel and the blue channel. And in a system like this, we have 256 options for those values. So we can have any value between 0 and 255, basically. And that is how we run our algorithms with the owl, because computers, they see in numbers. And at the end of the day, humans have a great, I guess, ability to see images and make sense of and understand contextual, I guess, environments and work out what's in an image and where it is. Whereas computers just have to deal with numbers. But that means we can also just perform fairly straightforward equations on these numbers to try and identify where green is in an image, which is how the owl works. And that brings us to the OpenWeedLocator. So the OpenWeedLocator is just a simple excess green, which was developed back in 1995. And that excess green algorithm just multiplies the green channel by 2, and then you subtract the red channel and the blue channel. So you think back to those matrices of or those large images before of just the pixel numbers. You multiply every single one of those numbers by 2 and then subtract in the green channel and then subtract the red and the blue channel from it. And that gives you the green area, but it amplifies it. And then you apply thresholds and do a range of other techniques to find out the area location of it. We also have other algorithms on the owl too. So we do hue, saturation, and value thresholding. That's another way of looking at color and intensity of color in an image. And together, when we combine these into, say, XHSV, which is one of the algorithms we provide on GitHub, we have excess green plus hue, saturation, and value thresholding. Then you can do things like green detection under a range of different conditions. But the major flaw, or I guess the drawback of these systems, is that they are very much dependent on relative color. So if you have, say, a change in lighting, or if the sun comes up or goes behind a cloud or there's a shadow, then sometimes those colors relative to the computer might seem different. And that's why I might get a false positive or a non-detection. Also, things like a sow thistle might be purple when it's under stress and there's a bit of drought around. And obviously it won't pick up the purple sow thistle because, again, it's not green. And that's why I guess why we get more advanced algorithms. But today we're just focusing on the excess green, hue, saturation, value, those kinds of simple, straightforward algorithms that make up the OpenWeedLocator. Because at the end of the day, the owl is meant to be low cost, it's meant to be accessible, it's meant for education, so we can show people how these systems work. And also, it's about development over time. So we start off with simple green detection, and then as William and Angus will explain shortly, then we'll start to get to more of those advanced, even green on green algorithms. And just quickly through the hardware. So this is how I guess it works. So you have the frame that comes in. The frame is broken up into 4 different zones about allocation. So this is post weed detection. Then each of those zones is allocated to a particular pin on the Raspberry Pi. So the Raspberry Pi has pins, which we'll see in more detail later. And each of those pins then activates a specific relay on the relay board, and then you can get targeted control. So it's doing full frame analysis and then breaking up each of the weeds into a specific zone, and then turning on a nozzle over that zone specifically. And now these relays could control a range of different things. At the moment, we've got them, as we'll see later, controlling solenoids for spray. But you could do it for a targeted tillage. You could have a tine that comes down and chips out that part of the image. And equally, if you go through the code, you can actually change the number of relays and GPIO pins that are activated. So it could be a single channel, or it could be even 6, 8, however many relays you want to fit. Obviously, that would change some of the hardware and the wiring as well, but that is all possible with the and so this is the design for the hardware. So we have basically this is the boom we'll see later, but this is what it might look like fitted to a boom. So we have 2 up top, each covers 1 meter, and then there's a nozzle every 25 centimeters. So you have a 25 centimeter spacing, so you can spot spray weeds. And that's something we'll see later in the car park. And this is, again, that software design. So we have the input image, we break it into its red, green, and blue channels. We also break it into its hue, saturation, and value channels. And then we have the different algorithms that perform or use this information separately. So going back to that image of different pixel intensities, we form with XG. So I think there's something weird happening with the going between Linux and Windows. But we do have XG, we have normalized XG, we have XG, and also HSV, and then HSV by itself. The algorithm will be running in the car park will be HSV, but William will go through that later. And then, of course, by thresholding, and that means you can work out where the weeds So now I'll hand over quickly to William and Angus.
Okay, so I guess I'll just introduce myself. So I'm William Salter. I'm a postdoctoral research fellow at the University of Sydney. And I guess I helped Guy to develop the OpenWeedLocator from a sort of hobby project to a true open source published piece of kit that you can now find on Github and also in an open access publication as well. And we are continuing to do some research with the OWL at the University of Sydney. And I guess that's where I introduce Angus McIntyre, who's sat next to me, who is one of our honours students within the group, who's working with OWL.
Hi there. So yeah, I'm Angus McIntyre, and I chose to do a project with the OWL system because I thought it was quite interesting, and it's sparked my imagination to see what we can do here. So I guess we're working on optimizing the OWL system without changing too much. So I think we're keeping the Raspberry Pi computer, but we're changing the camera systems just within that.
So we're looking at 5 different cameras, including sort of top of the range machine vision cameras to slightly lower cost cameras, including the Raspberry Pi V2 camera, and also just optimizing some of the settings that we have been using on the OWL up till now with respect to the camera. And that will allow us to operate the OWL at increasing ground speeds. So I guess at speeds that we could use in the field proper. And also dialing in for the detection of small weeds as well. We also do have another Angus, who's also an honours student within the group, Angus Malmo. He's looking at different chemistry options for spot spraying with the OWL in his project. And I guess ultimately where we want to see this going is to develop the OWL into a system that could be used for in-crop weed recognition. But I mean, Guy touched on it a little bit earlier, that the Raspberry Pi is low cost, low power, and we can run these simple color-based algorithms on it quite easily. When we shift to in-crop weed recognition, we're really needing to start thinking about more complex algorithms using machine learning and deep learning. And I guess just for a bit of context, some of the other work we're doing is using top-of-the-range graphics cards that draw in a region of sort of 400 watts of power to run these deep learning algorithms. When we were doing some testing yesterday with our OWL, it was drawing 12 watts of power. So it's quite a big difference there, and so we're probably going to have to, if we really do want to realize OWL for in-crop weed recognition, we do think we'll have to shift to a different platform, but that is something we're working on. Obviously, OWL is also a community project. We have now got quite a good sized community working with OWL on our GitHub. They have identified other areas for improvement with the OWL system, including designing an improved enclosure for the system that's maybe more waterproof, a bit more rugged, incorporating GPS into the system, having a bit more stability with both the software and the hardware. But I guess the possibilities are really endless, and that's where you guys come in. That we've let the OWL fly, and where it goes from now is really up to the agricultural community and the people that get involved in the OWL project.
Okay, so the next part of this will be the assembly. The idea with this presentation is we'll go through a few different sections. So we'll start off with just the component overview, so what we've got on the table here, and then I'll do the first, I guess, basic build of it, so assembling the components. And so I guess the first thing is that I should mention is obviously when working with electronics, there are some hazards involved. With hobby and DIY electronics, it's obviously less so than anything of higher voltage. And all that I'm working with here today is between or under 12 volts. The Pi only accepts 5 volts. And if you power with more than that, then you'll be in some trouble. And everything else that comes from the battery is 12 volts. But in saying that, when you're using any cutting tools or any things like that, you should always wear safety glasses. So I'll stick my safety glasses on. And I guess, yeah, get started. And the other thing is if you do, whenever you do power things on with a 12 volts, and if they're connected incorrectly, you can end up damaging your components. So make sure you are careful when you do power things on for the first time, and I'll run through that when I power this on. Let's start off with the Raspberry Pi itself. This is the Raspberry Pi 4, 8GB version, and this is currently as rare as hen's teeth. They're really hard to come by, but they do only cost about just over $120 odd. So there's a global shortage of these components, but this one was just fitted to the base of the Raspberry Pi 3D printed mount. So let me just take you through the GitHub, and if you are trying to follow along at home, just have this open in the background, and this will I'll be using this as a guide as well up on my screen, but I'll have the top-down camera obviously showing what's happening in front of me. And this guide should take you step by step through the entire process, and to get to I guess where we need to do the assembly itself is just down here under hardware requirements and hardware assembly. And so all the components that I've got in front of me are also listed under this table here. So these are everything you need to build an owl. And we've gone ahead and assembled some of these components, but I'll do the majority of the assembly underneath the camera here and live. And yeah, and you can get the links were provided to local Australian suppliers, but they're just suggestions and links to show what it is. If you're in other parts of the world, it makes more sense to get it from your local electronic stores or whatever is most convenient for you. And then to open up the hardware assembly, so here's the hardware assembly tab. Click on Complete Guide to Hardware Assembly, and that will have all the different steps to constructing the OpenWeedLocator. So this first image that you come across is probably the most important, and I always reference it myself because remembering all these different pin numbers and where different colors go, it's fairly critical. Because as I mentioned with the Raspberry Pi that we'll be using, getting these pin connections correct is critical. Because if you connect them, particularly the power pins, if you connect those incorrectly, you will end up frying your Raspberry Pi. And given they are quite rare and not expensive, but also $100, it's not the ideal outcome. So make sure you refer to this all the time. So the first step is the enclosure and mounts. We've obviously printed these, so you can see them in the top right of your screen. These have been printed on our 3D printer. We use a Prusa MK3 from 2019, and it's still going great. We'll definitely recommend those, but there are of course many others out there. We've also printed out the base, and all those 3D model files are down in the 3D model section. So if you go back to the top, then you click on 3D printing, take down to this drop-down menu, you'll be able to see all the 3D model files here. And they do take about probably 30 hours of printing. So I think the base and its components are about 12. I think the cover's about another 12. And then that should do it all. But then there's of course the intermediate parts as well. That's the 3D printing side. So scroll back up. And so yeah, I actually recommend doing those early and having them ready for your 3D to put it all together. You can also get them done online. So I've built ours where I've had the 3D printing. If you don't have a 3D printer, you can order 3D prints, and all you have to do is download those STL files and send them to the 3D printer. But that is a little bit more expensive compared to doing it yourself. But obviously, investing in a 3D printer is quite expensive too. So then, after we've got all the 3D mounts printed, I guess I should also point out we have the 3D printed backplate for the camera here, and also the 3D printed plate for the relay board. Then it comes to the soldering section. So I'll stop sharing and go back to the screen. Because soldering is I guess one of the most important parts. Again, not doing soldering live here, unfortunately. I didn't quite want to tempt fate that much. But what we found is soldering directly to this board here. This is the power board. So this is the Pololu 5 amp, 5 volt power converter, converts 12 volts to 5 volts DC. But soldering directly to those pins is much more rugged than connecting a set of pins like on the Raspberry Pi here with these pins that you can mount a connection to. you solder directly to the board, that's better. It doesn't fall off. You don't have any issue, well, fewer issues, I guess. But you have to be careful about heating the board up. But we've soldered those ones. The other soldering that's involved, you can solder the base of this. So to get power to all of the different solenoids that will connect to this, you do have to jump the input 5 volts to each of the normally open rails. So then when you connect each of the solenoids to the system, the power comes in through this red wire here, and then goes to the solenoid out. The colored wires will connect soon, and then connects to the other solenoids as well. The other soldering is on the relay, sorry, the fuse here. So we've done the soldering there, as you can see. Apologies. And that, again, you just need it's fairly quick and simple to solder, but just make sure you cover it with some heat shrink, so to avoid any issues. We've got a 10 amp fuse in there, but as Tam mentioned, it's only about 12 watts at 12 volts. So that works out to just over an amp of current. So this could actually be much lower. But that's a fairly important piece, so we don't try too many things if it does all go wrong. I guess the other final soldering piece is this one here. So this is the LED, the status LED. Yeah. But yeah, this is, I guess, most of the soldering that's been done. And I guess finally there's one more prep. You don't necessarily have to solder these, but I find it's better if you have, these are the wires that go from the Bolgan connector out or into the relay control board. And it's much easier to connect them to the relay control board and those terminals if they're soldered, and have a little, I guess, a bit of heat shrink around them to make it a bit neater. So I've done that as well. That's most of the pre-preparation. We've got some wires over here that are connections from the relay board to the Pi. We've got the camera, of course. We've got another LED that's a 12 volt LED. This is has a resistor in series, so it can run directly off the Pi pins. We've got some other wires here. This is for the power to the relay board from the 12 volt system. We have these Wago. These are 2 block connectors. And so these mean they're really simple ways of connecting wires quite well. And it saved a lot of time. And the idea with this is lots of these connections could be done with more permanent ways, but to make it more accessible, it's much better just to have these simple connections. And they're much preferable to, personally anyway, I find them much easier than soldering. You just stick wires in, again, we'll see later, but these are great. And we've got 2 of those, one for positive and then one for negative, but they are effectively the same thing. That's, I think, is most of the equipment here. We've got these are wire strippers. We probably don't need those today, but these are excellent if you are building one from scratch. We've got tweezers, which is great, use a lot of small parts. This is a M3 Allen key for our M3 bolts, and also a screwdriver for the Bolgan connector. We've got the buzzer as well. I haven't mentioned that. That's just, again, an option, added feature, I guess. It means you can know when things are turning on correctly, and that just connects to the pins on the GPIO of the Raspberry Pi. And the final thing is the version of the hour making is the single connector. It's called the single connector version. So it has a single hole in the back here, and that's where we mount the Bolgan plug. That's this one here. And so that makes it easier to take things in and out because you can disconnect it quickly. It's a quick connect and also IP rated, so it's dust and waterproof. But if you did just want to use cable glands, there's also a cable gland version too. So I think that should be most of the components now. I'll clear some of these off to the side of screen just so we can have some workspace. The wires over here, that'll be later on. The wires over there, camera off. And we'll bring this to the front. The cover we'll do at the end as well. And the stickers, which I got in the US. And this is the power supply, which we'll need shortly. And this is probably one of the first things we'll be working with. And also, one thing I will mention is we just recently, like the last few days, developed a fitting for this lens protector. So it means you can actually have a fairly sealed OpenWeedLocator now. So it just, again, this is the most recent version. This is just a 40 mil lens protector, and that just slots right in the base here. So you should be able to press it down, and that should fit in as a press fit. Again, if you're doing this more permanently, there are things I'm doing now that if you're doing a permanent version of the owl, you'd want to add, say, glue around here. And when we do the LEDs later, also a bit of hot glue would help as well. But this is going to be, I guess, put together and taken apart. So it's not necessarily a permanent one with all the hot glue that's required. But I will point that out as we go. And obviously, if you are building these, it will kind of make sense as well, where to put that glue to make things a little bit more sturdy. So the first thing we want to put in, this is our Bolgan connector, and it has a large nut on the back that bolts, sort of makes it fit tight against the back of the 3D printed housing. What we've done with this is, because it's quite a large fitting, we have clipped off each of the flange, I guess, that was around it. So if you look at that carefully, you can see where it's being clipped off. So if you are doing this with a Bolgan connector, and this one specifically, you will need to do that to make it fit. That will be quite obvious when you're trying to put it in and it doesn't fit. So if you get this, put that in like that, there is a directional thing on it. So, and this fits the cutout on the, as you can see here. So fit that in the top there. Basically this goes towards the top, and now on the back, you want to then tighten this up. So we're now got the Bolgan connector in. The next part is to put in the relay, sorry, the fuse holder. So again, key thing with this, make sure there's actually a fuse inside it. There's been times we've started an owl up and sort of scratching our head why it won't turn on. We've checked all the connections, and then probably Williams made the suggestion, oh, have you actually put a fuse into it? And I'll be like, no, I have not. And put a fuse in, it works great. So make sure you do that. Because it does get quite frustrating if you're trying to work out what's wrong. It's just the back of the fuse. So put that in through the hole, just the largest hole, just to the left of the, well, if you're facing it to the left, in this camera, I guess it's to the right of the Bolgan connector, and then push that all the way in. On the inside, you want to have a look at where these wires are going as well. So just make sure they're on the other side of this mount for the relay control board. Push that all the way in, and then we also want to tighten it up. So the fuses usually come with this nut as well, similar to the one on the Bolgan connector. So thread that down here. Thread it onto the fuse, might need to push back out again. And then tighten it up. And this just improves the waterability, I guess, so waterproofness or durability of the owl system. You want to tighten it all the way, so it's press fit against it. It also means when you do take a fuse out or change fuses, that it won't twist the wires inside as well. And that should be fairly sturdy now. I just want to make sure that's orientated correctly. So you can see in the front, it's slightly off center. So we'll just rotate that a little bit and tighten it up again. And then now check our connections are coming off correctly. Maybe just push them out of the way. And I'll thank Angus for doing all these soldering for me. So now they're out of the way. These two wires should be all good. The next step is to add in the Bolgan connector. Again, the order of all this is fairly critical, because if you connect this into the Bolgan connector, you can't get access to these screws to actually connect the positive wire to. So basically what's happening here is this is where your power is coming in from your 12-volt system. It's going into the Bolgan connector, coming to the fuse, and so the fuse is the first thing in the system to blow if there's a short circuit somewhere else. And so that's why this has to be connected to this first. And also we want to make sure that when we don't click it into the Bolgan connector and then don't have access to these screws, so we can't actually connect it. So the last few days I've made this mistake lots of times where we connect things before or not in the correct order. So make sure you're doing or putting the wires through the right, I guess, fittings before you wire them in and have to undo them and correct it again. But anyway, so put the ground wire through here. And then you should be able to see that ground wire coming out of the side. The other wires here, so these go out to the solenoids, or to the relay board, I should say. They just sit in the middle. But what we need to do is thread this one. This wire we'll use for the output. So what power will come in here and go out here. And then we just have to thread this one through to the other side. And this is where it does get a little bit fiddly. And so I'll just twist that a little bit. And that is a little bit long. So I'll just get my wire cutters, and this is why I have safety glasses on. We'll just clip that wire, and so it's a little bit shorter for the Bolgan connector. So the Bolgan connector needs about probably 4 or 5 mil max of wire, otherwise it's too big for it. So cut that off. I'll put these to the side. and I'll get my flathead screwdriver. And you can see that this connector here is number 5. So positive goes to 5 and negative goes to 6. That's probably the most critical distinction here, because if you're connecting up the wrong way, you will burn out everything. Anyway, so unscrew it a little bit so we can see. And these are quite fiddly. So apologies to see the top of my head. So we thread that into the bulb connector. You might need to more. There's also quite high gauge wire as well. That should do it now. So then if we thread this into the connector, that should be in. Then we just need to tighten it down. Again, just screw that in. Make sure it's nice and tight, because if it falls out, that's less than ideal. So give it a gentle tug and it should, that's in there pretty good, as are the rest of them. All right, so that's probably one of the more fiddly stages done, which is good. So then what we can do is push this bulb connector into the enclosure. So you'll see that as I'm doing this, I'll get out of the way. All these wires should come through, and this is where we might need tweezers to pull them out. So we'll grab the wires as they come through. I think the green one's being put up. There we go. Just pull these out. Now you can see all the wires are coming out the other side. So we've got the black wire for ground, and we've got relay number 1, which is blue, number 2, which is green, number 3, orange, and 4 is white. And that also matches the pin numbering on the bulb connector as well. So then to finally fit this connector, we just have to rotate it until the keyway lines up, and then we just push it in until it clicks, and that should be locked in. So that is one step done. So we've got power coming in to the fuse, and now the next stage of this build is to add the relay control board. This accepts information from the PI. So this is 3 volts high and low. So a relay will turn on when it receives 3 volts into that channel. So it's got pins on this side and also output pins on this side. So these go to the solenoids. This takes 12 volts in and forms the connection when the relay is switched, and each of them operates individually. But they do have to have this common channel. So this common channel means you can share that 12 volts between all of the 4 different solenoids. There are a range of different boards. Be careful when you buy these. Some are active low instead of active high. Basically, it will turn off. It will do the opposite of what you would hope it should do. The other thing to note is that on this one here, we've got it connected to all the normally closed fittings. So on the side, we have NC, normally closed, common or COM, and normally open on these ones here, as in they're not connected when there's no power to it. Then there's common, and then there's normally closed. So they are connected when there's power to it. So we've connected the 12 volts to each of the normally open pins, and then we'll connect each of the relays or the solenoids, these wires down here, to the common pins. It doesn't matter if you connect one to the other. It's just, yeah, as long as you're consistent and you have each of these connected to either common or normally open. With that being said, let's start doing that. 20 minutes in. Okay. So we'll put this, we'll leave one of these wires underneath, so that keeps it out of the way. And then we'll fit in the relay this direction. Again, one other thing to note is the relay needs to be this way, because the power board, which will attach now, has to be on this side. There needs to be room for it to fit along this side of the hour. So it fits like this. And if you orientate the base, this plastic part, the 3D printed part, the opposite direction, you rotate this and mount it off the other way around, it means when you fit this, it will actually be butted up against this side of the housing, and there won't be room for this this power supply unit. So that's the next stage. We'll get the these are 2.5 millimeter pins, and they fit through the relay control board. You can either use 2 millimeter for the power unit here. So these are actually M2.5. You can get them through just, but they should be 2 millimeters, but you can get away with using 2.5 as well. We use nylon, these are plastic. You can also use brass, and I would recommend using something like Loctite to keep everything together if you're planning on using this. And to the far left corner here, so this one, we'll screw that in there to the mount. Fairly fiddly. Once that's screwed in, we do have a spacer in there as well. So depending on the length of your screws, will change if you need a spacer or not. We've added a spacer just so it's long enough to get through the power supply and also the relay board, but not too long. So now I've got the power supply or power converter, 12 volts to 5 volts mounted. Got the relay board in its position. The next step is to wire up the relay board. So we've got to connect all these wires here. Leave this negative wire out the way for the moment. And as I mentioned, we'll definitely refer to the GitHub as we go along. So just make sure you're following along that if you like as well. I'll try and keep to that as much as possible. So as I mentioned, blue is relay number 1. We're consistent with colors throughout. So blue is always 1, and this relay here is relay number 1. So I'll attach that to the common. So we've got to loosen up the connection first, and then feed in this blue connection. That should just fit in like that. So once that's in, it is fairly tight. So then we just tighten that down. Sorry if you can see. Tighten that down. And we should be check, and that's give it a pull, and it should stay in there. The next one, orange, is number 2. So it fit. What we're doing is just putting each of these into the relevant or appropriate relay connections. Stick it in there, number 2. Hold it in, and while we're doing that, just tighten it down. Green is then number 3. So put green into relay number 3. Again, the common pin. We do mention on GitHub as well that you can solder wires underneath this and make it more neat. But to make it more obvious for this demo, we've put them above. Can just check that's in properly. Yes. And then finally, white is number 4. It's the last one here. Can sometimes I prefer to keep them all above each other. So we'll bring white across and just thread that into that common as well. So it's difficult to get the top-down view of it, but should be able to see that white wire there is now in the center from the common position for the 4th relay. Tighten that down. That's pretty tight. Now check them all again. They should all be in. Nice. All right. So that's in, that's on. We've got most of the power and the relay boards done now. So what we can now start to do is connect up these Wago connectors to the positive terminals. So this is the power coming from, this one here is from the relay board, and this is, sorry, from the fuse, and this is from the relay board. And we can, if we connect them together, I might actually need to lengthen that a little bit. I'll get my wire strippers and just strip the wire off here. That's a little bit longer, and then fit it into the Wago connection terminal here. You should have to make sure, so when you go inside it, you see there's 2 little sort of gaps there. Just make sure you thread it through that gap well. And then so it should go all the way to the back. And then once they're in there, just flick that down. So it should go down all the way. And then just again, just double check they're in there properly and pull them. Well, this is also the power. So now this is our power junction, I guess, the little junction box. So we need to distribute this power. Firstly, going to the relay board. We also need to send it to this board here as well, the power supply, or power converter, I should say. I'll wait until we need to put a couple other things in first. So I'll wait until connecting this, because you can put multiple into the same section without disconnecting and connecting all the time. But basically, the way I do it is, as we get more wires to attach, I fit more into this, the block. And sometimes you have to redo it a few times, but we should have a few wires each side. So I'll just wait on the moment before doing these. but we can, wait until we get a few more negative wires as well. We've got that side sorted. So the next stage in the process is actually starting to put the Raspberry Pi in. So this is the Pi, got the GPIO pins, general purpose input output pins on this side. And then you've got the input for video and other things on here, and your Ethernet, and then 4 USB ports here. The way you want to orientate it, again, this is just mounted on that plastic board again, we've done that already, is GPIO pins towards the back or towards the camera, and these display pins here. So fit that in, and leave a little bit of room around it. You may need to move it at some points as we put cameras in, but we'll just put it there for the moment. And now we can start connecting pins from the relay board to the Pi itself. So that's when these wires start to come in handy. I also just put these are the 12-volt connections for the relay board, which I might as well do now. So on the relay board, while we're talking about it, there is a pin that says VCC, which is voltage or positive side, way up the top here. So it's this one, that one just there. It's typical with this resolution. But basically you see the VCC and grounds, you want the black wire to the grounds and the red wire to the VCC. And so we'll fit that on. And that's just another one of those positive wires we need to attach shortly. I think we probably have enough. We'll connect a couple of our negative wires here to that Wago block. So we can twist them together like that. Get that Wago lock and put them in, and then close it. And then just give them a short pull, make sure they're in there properly. All right, that's in. So we've got, this is now powered. So it's connected to the fuse holder through these blocks. And now we need to connect our pins for the relay board. These, I guess, go up in order. So you've got in 4, in 3, in 2, and in 1, and common. So common goes to the ground on the Pi. So we'll put our brown wire there for common. In 4, remember, it's white. So the 4th relay is controlled by this wire. We'll put that in. We have also the orange wire, which was the 3rd relay. So I'm going to head out the way. We have the green wire, which is the 2nd relay. And the blue wire, which is the 1st relay. A little bit hard to fit in. We'll take out these ones for the moment. There is some juggling you have to do as you go through this. And then we'll put this VCC and ground back in, just double check the orientation of that. So red's on the outside. Okay, so now we're back. So we've got all these wires connected to the relay board. Now we need to connect them to the Pi. So I'll just quickly tab across for me to the GitHub and just look at where each of these pins go. So COM, which is our brown pin, that goes to, as if we track it along, that goes to pin number 14. And so on the Raspberry Pi, the pins closest, or the inside pins, they're all your odd pins, and the outside ones are even. So number 14 for the common will be 7 pins down on the left side. So 1, 2, 3, 4, 5, 6, 7. So it should be this pin here. That should be pin number 14. We'll just double check. So it's 1, so 2, 4, 6, 8, 10, 12, 14, 3, 4, 5, 6. All right, so that common one's in. So after that, on pin number 13 is the blue. So we go back here. So blue in number 1 goes to pin number 13. That makes sense because it's the first one off, and it goes to the lowest number pin. Probably. After that, we have green. Green goes to pin number 15. So 13 to 15 is just next to it. Then we have pin number 16, which is the orange pin, which is just opposite pin number 15. And finally, we have the white pin, which is pin number 18, which is just next to that. The ordering of these pins is fairly critical because this is what the software tells to turn on or off. So you have one connected to say pin number 20 or 20 is the ground actually, so you gotta be careful there. Then that's not so good, so it won't work. But that's all our communication pins and our COM pin connected. Let me just tab back. You should be able to see them connected just there onto those pins there. But as I said, make sure you go to GitHub and follow that diagram. I probably should keep on trucking on here as we get to decent distance into our time. So we'll connect the power to the Raspberry Pi. That is the coming off the 12 volt to 5 volt system. Still got a couple of spare wires here. We'll connect later once we put the other accessories in. But for the moment, we've got the substance of the owl in. So we've got the relay and the Raspberry Pi. The final piece of this system is the camera. And then we'll get on to the more of the, I guess, accessories like your lighting and buzzers. But we'll just, I guess, neaten these up a little bit. And we'll get the camera involved. So much unplug that for the moment. You do have to shuffle things around as you go. Now, the camera. So this is one of the more recent mounts, and I'll be using M3 screws here. These are M3 Allen screws. Undo those. If you have any questions, make sure you put them into the chat or feel free to jump online I guess through the voice as well. This is the ribbon cable for the camera, and that should go under the owl, and then you can feed it up towards the back. So rest this down for the moment. Now tweezers, and then bring the ribbon cable up the other side, and then you can put the Raspberry Pi back down. This needs to be connected into the camera slot on the Raspberry Pi. This one just here. So put that in, and then press down that black bar to lock it in. That looks like it's incorrectly, and then now we can actually physically connect the camera itself. And the other important thing is getting the orientation right. So the camera, the mount has to be facing closest to the Pi itself. And we'll just like that. And now we have to connect it with these screws. So I'll just put one screw in the base, like so. Push it through. Get our Allen key out and start tightening this up. Just check it's seated there. In the interest of time, I think I might just do 2 of these. But obviously, if you're doing this properly, you'd want to make sure they're all 4 are in. Again, push it through. And tighten that in, make sure it's aligned on this side.
So Guy, just whilst you're tightening those up, we designed that mount recently to also be used with a very cheap V2 camera. So if you did want to also use a cheap, make a cheaper owl, it would run with a cheap V2 camera, which I think costs about $30. You would just need to use smaller standoffs, but you wouldn't need any code changes or anything like that to make that work as well.
Yeah, that's exactly right. Lots of these, the Raspberry Pi is one of the major benefits is that you can interchange between different cameras quite easily. And the original design, yeah, of the owl was with the V2. So I think that's all 4 of them almost in. All right, so that's for what is most was basically the owl almost completed. So we just need to do the final wiring. So now with the camera in, the camera's connected, relay board's in, it's connected to make sure it's sitting flat and there's nothing pressing hard against too many things. We just got to do this is the status indicator that goes to the transmission pins and the ground pins on the Pi, and then also the 12 volt LED to say that everything's on. So we'll do that one first. This just goes into the hole on the just adjacent to the Vulkan connector. So I'll fit that in. And then it also goes into these plugs here. I'll just leave them up for the moment. Actually, that is the very last one. So we'll get them all wide in now. So all these three here do need to go into that second part of that block. And this is where it does get a little bit fiddly. Just thread them into the block there. And then close that down. And they should, there you go, they should be locked in there properly. Then just double check they're in. And now we do the same for the negative terminal. So take this is the connection to the solenoids, or to the 12 volts outside. And then just connect that to this negative block here. And this is a much easier and faster way of connecting lots of terminals quickly. Push into the back, latch it down, double check they're in properly. Oops, see, this one isn't in. So we'll just have to redo that one. In. Doesn't want to go in. So we might have to wire these together. Sometimes you have to twist them as well. All good. And third time's a charm. All good. Okay. So now we're all wired up on that front. So we'll tuck those away. We're wired up here this front. We can, I'll leave that, that'll be the last thing we'll do. And we can connect, well, firstly we can do the buzzer. Again, go back to the GitHub and check which pins the buzzer goes to. And the buzzer goes to pins number 7 and 9. 9 is the ground, 7 is the active high. So what the buzzer here, black and white, black and red. So pin number 1, 3, 5, 7. 1, 3, 5, 7, and 9. So there should be one gap. Remember 9, double check that. 9 was the ground and 7 was the active. So 1, 3, 5, 7, 9. I always just double check these things because they go wrong. It's not great. Although with the buzzer, it's not the end of the world. It's all the other things. So finally put the status indicator in. This will tell us when the Raspberry Pi is actually on. So feed that into the other hole just next to the power indicator. And if you were doing this properly, or I guess for more permanent situations, you want to hot glue those in. And then now we've got 2 wires here, and we'll just double check that wiring diagram again. And so the LED goes into pins 8 and 20. So 20 is ground, 20 is just adjacent to the final 18 pin, number, the white one, and 8 is just opposite number 7 there. So 20 is ground. And then 8 is just opposite number 7. So 2, 4, 6, and 8. And there you have it. That is 1 owl assembled. You can see the final pins I've just put in there. So that's the owl. I'll just wire in the Raspberry Pi. So this is the, sorry, the lights have gone off in the room here. There you go. So there's the actually mostly complete Pi. So final things you want to check, make sure your power's in correctly, make sure these are all wired up correctly. We've gone through and checked those. The light is on, the camera's in, connected. Your power board is connected over this side, and that is connected into these connectors here, the 12 volts in. Then your lights are on, lights are in and connected. Your fuse is also in, and the bulb and connector is also plugged in. And now for the moment of truth, we can plug it in. So you should hear a faint beep. You should then see, I'll use this camera here. You should see this light come on. This is the 12 volts active. This is the Pi starting up. You'll see green lights just on the Raspberry Pi here flashing. That's your status pin. That's connected to this LED here. That beep will go away if it starts correctly. So this is like a faint humming, I guess. There you go. And so now it's on. You should be able to see the OpenWeedLocator on the screen. And you'll be able to hear those relays clicking because it's just sitting on this white surface as well. Okay, it's getting I'll leave that clicking around in the background. It doesn't like the inside lighting. It's designed more for sunlight. But I'll just now take you through the way we designed some of the software and how you can change it yourself. So you should be able to see that screen there, hopefully working out all right. And let me just turn on. So when you're doing this at home, you'll need access to the internet, to the Pi, so you can connect it to your local network or plug it in via the Ethernet cable. So I'll just connect it to the to local Wi-Fi here by phone. And what we can do is then actually download and update the software on the Pi. So this is obviously being flashed. There is, if you go to the GitHub itself, the next step is to get a SD card. This is obviously an SD card adapter. It has to be a micro SD card, a brand new one. And if you go to our GitHub page, this is an interesting way of screen sharing or literal screen share. But you can, sorry, typing on the wrong keyboard here. You should be able to download the basic version of the OWL image if you want to do the fast setup. So what we can do is to go to software installation, but basically the software installation you can do in a couple of different ways. So we have either a quick method, which basically you download our disk image. So this is about a 6 GB, 7 GB file, and it's what we initially developed. So you effectively just, you can see or use the original OWL specifications. It's a very original version. We do need to update it. And some of the code we've since fixed and corrected aren't available on that image. So it's something we need to fix and probably we'll do over the next few weeks. But the next part, I guess, is to update that image with the most recent repository. But once you've downloaded that disk image, you can then flash it to an SD card, which we've already done. So we use Ballerina Etcher. It's just a file, and this has to be done on a laptop. So this can't be done on the Pi, but it just needs to be done on a separate laptop. And then you flash it to the SD card. And then once you got the SD card, you take it out of the separate laptop, and then you can put it into the Pi. So I've sort of skipped a step here, I guess, a little bit, sorry, in that we've already started up the Pi. I was nervous to get that done. But most of this up to this point is done on a separate computer. So once you flash the SD card, it's ready to put into the Pi. So even though it's a basic version, it still has everything. It'll get it up and running. And you should hear, once you power it up, as we didn't hear those that double beep indicating that the software is running correctly. But as I mentioned, because this is now on the Pi, step 3 onwards is on the Pi. So this is now on the right path. You didn't update it because the software is a bit older. It still works, but it's just not as refined. It has some probably more issues with it. So to update the software, we just open up terminal. So this is a terminal window. You can either click this top left here, or you can press Control-T on your keyboard. And then once you've got terminal, this is a way to control the Pi from the command, what's called the command line. And so basically what we're doing here is you name, if you go into the file system, you've already done it, we name the old software OWL space old, and then we download the new software and then rename it. If you go over here, we download it, git clone, this clones our repository. We change the name of OpenWeedLocator to OWL. We move into that folder. We pip install requirements. This is the fairly important part here because we have had some issues with the versioning as different versions of software change that are required to run our software. Then we make sure that again, this is a pretty key part here, we make sure that each of these are actually running properly and can be run on boot. So sometimes you have to make sure files can be run by the operating system as opposed to us doing it manually. So this is where chmod means change mode or similar, I guess. And then you can both read it and write it. And that's the file we're going to change, and also the OWL boot. So it can start every time you launch it. You don't have to change it with a screen connected. Then you can also focus the camera. And so one issue is with focusing it, you do need to stop what it's currently doing. So at the moment it's still running, as you can sort of see, I guess, in the background. So we need to cancel that, which is what we need to do right now. And so to cancel it, we need to check, I guess, what is there a process actually running currently in the background? Because the way we run this on boot, it's probably a little bit technical, but I'll sort of go through it. The way you run it on boot is to run it through what's called a cron job, and that will continue running in the background unless we stop it. So we can see everything that's running on the Pi on this screen here, and I ran this command ps axjf. That'll bring up everything that's running. So then we have to scroll down until we see this line here, which is the green on brown.py. And so we go scroll across until we see what like program ID it is, or PID, I think, is number 532. So then we can go, we scroll down to the bottom, and what we can type is sudo kill 532, because it's currently running. And that should stop that process happening, and now we can actually start the next process. If there are any probably developers out there, I'm certainly no Linux expert, and I possibly made a lot of rookie errors, but this way seems to have worked. So if you do have more suggestions on a better way of doing it, please let me know. But now we've got it stopped, we can try running it again, and to start focusing the camera or start mucking around with the software as well. And so this is this part here. So now we go back to Raspberry Pi, we work on the OWL environment. So if you do the detailed methods, you'll start to understand some of these other terms you haven't come across them before, like environments and virtual environments. And basically what we do is we install the software within the virtual environment. So it keeps everything contained. And we call that environment OWL for obvious reasons. But that's when I say work on OWL, that's what's happening. And so if you are interested in learning more about it, I recommend doing the detailed method of installation. It does have a few more intricacies to it and does take a bit longer. But for me, it's, I think, well worth doing if you think you'll be working with the OWL longer term. I'll go back to the terminal window, and so I'll type work on OWL, and that should bring up on the command line here OWL brackets pi at Raspberry Pi. So now we know we're in that environment. Apologies for the tripod in the way, but the important stuff is just down this part here. And now we're on working or in that folder, or I guess in that environment, sorry, we can move into the OWL folder. And to make sure that is available, we can press ls, which lists all the folders in that directory we're currently in the home directory. And we can see that OWL is there, as well as OWL old. So we can press cd, which for change directory into OWL, cd OWL. And you'll see OWL now appears in the command line here. So now we're in OWL, we can actually start running the software. So we can say /green on brown .py. And because we made it executable when we went chmod, so change mode, it means we can run it with /. Otherwise, you can just type Python and then space and then the name, but it is executable, so we'll run it like this. And we do have flags now, so we did change the software this week, and so you can actually do flags on the command line instead of having to change the code. So we can type in show display, press enter, and then this should bring up the camera feed. So you hear it start beeping, and because we're inside, and I did change the white balance settings, you can see it's picking up these white bits on the floor, which is not ideal. But that's because it's inside, we're under fluorescent lighting, and it's not really meant for that. But obviously, when it goes outside, it does seem to perform better. And also, again, it's the intricacies of using color-based systems as opposed to more advanced deep learning algorithms. But this is the camera feed. It's quite well focused at the moment. If you did want to focus it, you just need to change the focus on the lens at the front here and adjust that to suit the focus, this focal distance that you're using. We work on just about 1 meter off the floor. And as you can see, if I get a green container, yeah, see it picks it up quite well. So that's the green detection. And you can see the nozzles turning on and off, and it tells you which nozzles are turning off in the background there as well. So we can also change different flags. So if I press escape, this will turn it off. So we have show display. We can also do algorithm selection, and we can change between HSV, or we can change algorithm to XHSV. We have a range of different options for us. Let's try XHSV. As this will be running a slightly different algorithm to before, and perhaps a little bit less sensitive to false positives, because it uses a combination of XG plus, as you can see, it's probably a little bit less sensitive, but it means you get fewer false positives. As you can see, you can just change algorithms fairly easily there. If you do want to actually check the code itself, you can navigate to the Pi folder. So open up a new directory and click up the top left here, or just open up the folder, go into OWL, and this is where you will want to see behind the tripod. Go to green-on-brown.py, go open, you don't execute internal, you just want to open it, and this will open it in the editor here. And so this is all the code that you can see on GitHub, but this is the code is actually running when we press play. So these are all different algorithms that it does. So you can see we just ran XHSV. So when we told it to run XHSV, this is what it was doing. But if you scroll down to the very bottom, you can spend time looking through this code if you like, and seeing how it can be improved or change things, or just getting familiar with Python. You can see some of the features we can change down here. These are also up on GitHub as well, so you can see what things you can adjust. So the sensitivity is all managed by these numbers here. So minimum, maximum XG, Q minimum, maximum. Again, because we're using thresholds, decreasing the range reduces sensitivity, whereas if you have a really big range, it'll detect most things. And if you look at hue color wheels, this is where the green color seems to fit. And then you can kind of try and avoid those maximum saturation, which is often in bright reflections or stubble, or maximum brightness, which is again often bright stubble or reflections from stones. You can change resolution, you can change sports mode. So at the moment we have it set to exposure mode. At the moment we have it set to sports, which hopefully increases shutter speed. And it's something that isn't present on that original image. So make sure you try and I would recommend changing that. But I think William and Gus are probably down at the field. So I might try and hand over to them.
So here you can see we've got a boom set up on the back of our ute at the uni here. On this system, we've got two owls set up on a 2-meter boom. So we've got 25 centimeter nozzle space in here. And here's another owl with the cover off. But yeah, we just welded up a mount for the tow bar here, and we've got this boom on the back. So we've got 4 nozzles for each owl unit, and these are controlled by the relay board that you've installed within the owl itself. So your red board here, which Guy showed you earlier. We're just running it from 12-volt power, which we have in the tray of the ute. So we just have a 12-volt battery here, and just a spray pump running, a spray tank with a 12-volt pump running. And so what we'll do now is we'll just fire it up, and we can hopefully give you a live demonstration of how it works. So we have just an on-off switch there, which Gus will flick for me. And you'll hear that faint sort of buzzy beepy noise whilst the system gets set up and running. You'll notice on this boom we also do have some 12-volt work lights, so that we could in theory run this at night, or if it's overcast, or at dusk. So yeah, hopefully that mitigates some of the lighting conditions that we can use the system under. It is actually picking up some small grain waves here, and so that's why you'll hear this spraying at the moment. But I also do have Angus here, and he's just going to show you how the system runs by just running a weed underneath the camera there. We also do have a light on each nozzle. That's sort of more for demonstration purposes, but hopefully you can see that that we are activating a nozzle as we pass under each sort of lane that we have in the OWL software. So yeah, that is the system in action. And now I'm going to get Gus to fire up the ute, and we'll show you it moving along and spraying on the fly. Initially, Gus is going to go at about 5 kilometers per hour. But then we're going to increase that speed to 10 in the second run and see how he goes. And that is one of the big one of the big aims of Gus's research project at the uni. In that he will be looking at mounting an OWL system and running it across transects at different speeds, and looking at how well the detection accuracy is going at different speeds. So yeah, Gus, whenever you're ready. Now I'm going to run along behind it here, and you'll see that we are spraying weeds on the ground here, and we're clicking on and off. And saving a huge amount of herbicide in the process. As you can see, we have quite a nice dusty road here, so hopefully you can see where we're spraying the weeds. So yeah, and so what we'll do now is just reverse the car back, and we'll do one more run. And just see how it goes at slightly higher operating speeds as just a final aspect of the demonstration here. I hope you'll see there that we are picking up the weeds and doing quite a good job at spraying them, even at that slightly higher operating speed. So I think that was probably at about 10 kilometers per hour. In his test, we'll be going up to probably 20 or 25 kilometers per hour on the back of the tractor.
The GitHub does have a discussions page, which I'll just share finally before we finish up. Go to the discussions page at the top here. You can start any discussions if you say build one, or making a change or want to talk about something, feel free to add something in here. And this is where we've been talking recently about redesigning the enclosure. So if you'd like to contribute or just want to have a comment or have a chat about it, feel free to post up in the discussion. But thanks again for everyone for joining. It's been an absolute pleasure. Glad everything worked out as it did. It was certainly a bit of a risky one, but very much appreciate your interest in the project. And yeah, looking forward to seeing some owls built everywhere. Thank you very much.
Thank you, guys.